So next in mechanics, we're going to start looking at something a little bit different compared to what you're used to from grade 11. We are going to start looking at this type of thing where we have something moving in a circle. So we're going to start looking at circular motion, which has some definite differences between regular motion you guys have done as compared to this type of thing. So it's a very specialized kind of motion. There's some really, really neat things that we can do with it. Some of the measurements are very similar, like speed and acceleration, that type of stuff, and forces involved. But it's a very special type of motion, and it can be used for lots of different things. It is actually used for tons of different things, whether you realize or not, and we'll look at some of those things as well. But it's a really, really nice, specialized kind of motion. It can be used for many applications because of its certain attributes. For example, if you have something like this, it's moving, but overall it doesn't really go anywhere. It's a very fluid kind of motion where there's no starting and stopping. If something's spinning, it can actually have motion, but not actually going anywhere. There's lots of different things that actually kick in with circular motion that we can look at. So we're just going to start looking at some of the basic properties and basic quantities of things moving in circles and see what kind of measurements and quantities can come out of it. So we are looking at good old circular motion. So we're going to start looking at circular motion. So like I was saying before, it's kind of unique, it's kind of special. Now, one of the things about it, it's a very efficient way to actually move. There's no starting and stopping. You just keep on going. Now, I mean, traffic is a great way to think about this. One of the most inefficient parts of driving is starting and stopping. It's way more efficient to use things like roundabouts and stuff like that when you're trying to change direction, because you don't stop and lose all of your momentum and all of your energy, then have to try and get it back. So circular motion is very, very efficient. You don't have to start and stop all over again and lose everything. Okay. There's some other things that actually make it really good as well. You can actually move, but sort of not move, which sounds kind of weird, basically when you spin. So like when you have something spinning, it can have motion and have all those things that go with motion, but not actually be going anywhere. And when you can spin things, you can often spin things to give them stability or store energy and stuff like that. And that comes along with circular motion as well, but the object doesn't actually have to go anywhere. So you can move, but not actually move anywhere, which is spinning. It's very, very efficient. There's lots of different kinds of cool things that you can actually do with it. So it's also great for things like transferring energy from one place to another, or transferring motion, like in gears and like motors and engines have spinning parts all over the place. Tires, there's lots of different things that's actually used for. So we're going to start looking at the whole circular motion thing and some of the basic properties and quantities involved, and then try to apply to certain situations. So let's just start by looking at some of the basic quantities or properties that you would have if you are moving in a circle. Well, let's start simple. If you are moving, you have to have some kind of speed. I mean, that's just really, really simple. So for the speed that we are going to use, we are going to assume that it is constant. It's just a lot easier. It's not realistic, but we will assume a constant speed for pretty much everything that we do involving basic circular motion. Now, if we are talking about basic speed, well, that's simple. I mean, the simplest, easiest way is just use dTV. That's the basic way to do it. Now, the thing is, if you're going in a circle, what we're going to do is we're going to specialize this. What we can do is we can specialize the situation a little bit. We can specialize the distance. If we're going around in a circle, the distance would be the distance around the actual circle itself. So what we can do is instead of using, regular distance, the distance around would be the circumference, which of course is 2 pi r when you're going around a circle. So we can specialize this by putting in 2 pi r as the distance. Now the thing is, if you use the distance to go around once, you also want to use the time it takes for it to go around one time. And when you talk about the time for whatever it is, one time around the circle or one time for anything, so the time for any one event, you've actually done this before in grade 11. the time it takes for one event or one thing to occur, that was the period from grade 11. And you guys took that in your waves unit. And if you remember, the symbol for that was a capital T. So we can specialize that as well, where you've got the distance specialized as 2 pi r, and you've got the time specialized as the period. So we end up with the speed is going to be 2 pi r divided by the period. Now, if you also remember from grade 11, there was another quantity that was actually directly connected to the period, and that was the frequency. Okay, so we'll talk about that as well and connect that to this. But let's just sort of put this in here. The period in here, of course, the period. And of course, this is the time for one event. Just trying to list them all together here. Okay, now, like we just talked about, that is directly connected to the frequency. Oops, gotta clean that up a little bit there. Frequency. All right, so we got the frequency. Now, if you remember from grade 11 waves as well, that period and the frequency had a direct connection to each other. This was actually the inverse of the period. The period was the time for one event, where the frequency was how many events or how many things divided by the time. So these two things were actually inverses of each other. So if we go back to the speed expression, we have the distance divided by the time. Dividing by the period is the exact same thing as multiplying by the frequency. So we can also write this as 2 pi rf. And just with this alone, basic DTV and a couple basic quantities that we introduced last year, we've got some of the basic quantities used for something going in a circle. We've got the speed going around. We got the circumference, which is the distance around, and then we got the period, and then we've got the frequency. And this expression that we have right here, 2 pi r of a period or 2 pi rf, is a really, really common way to find the speed of an object going around in a circle or something spinning. That's why if you look at things that spin, especially like machines and tools and stuff like that, or engines, one of the most common things actually listed is the spinning frequency of it, whether it's in RPMs or anything like that. The frequency is a really, really common way to tell you the speed of how fast something is actually spinning. All right, so that's the basic idea behind circular motion in terms of calculating the speed. Now, of course, there's other quantities as well, but we'll get to that later on. All right, let's just practice with this a little bit and see what else we can get into. Okay, so let's take a little question here. I can actually draw a circle relatively well. There we go. That's not too bad. All right, so let's say we've got somebody and they are running around a circular track. Okay, so maybe they're running around and they go around the track. And let's say they go around the track. Let's say they go around the track 25 times in, let's say, well, let's go 30 minutes. Okay, so it takes them half an hour. Okay, so we're going to go around this track 25 times in 30 minutes. And let's say they're ripping around. Let's say they are going 2.6 meters per second. All right, I want to know how wide is the track. Okay, well, let's just do some basic stuff here, no big deal. We can find a few things. Of course, one of the first things we want to take care of is that 30 minutes. We don't want to use minutes for anything. We want to, of course, change that into seconds. And if I change that into seconds, that would be 1800 seconds. And that's all taken care of. Now, there's a couple ways we can actually do this question, but we'll just take it one step at a time, no big deal. All right, so I've got the 25 times, I got the 1800 seconds. So with that 25 times 1800 seconds, I could either find the period or I could find the frequency. It doesn't really matter because it's really easy to go from one to the other. I usually try and go for the frequency. And of course, frequency is how many things per second. So I've got 25 times around in 1800 seconds. So I just have to divide those two out. and I will get the frequency, which is about 0.14 hertz. Okay, so there I've got the frequency. I've also got the speed over there. I've got my V value right there, and V was equal to 2 pi r f. Okay, so with this, I can, well, there's a couple ways you can do it, but I've got the V, I've got the 2 pi, radius could come in handy. So I can just solve for the radius, which would be V divided by the 2 pi f, and I can calculate the radius of the path. And with that, I get around, looks like around 30 meters. All right, so if the radius is 30 meters, of course, how wide would be the diameter? All I'd have to do is double it, and the path would be 60 meters wide. Okay, and that's pretty much it. It's a really straightforward basic calculation. I mean, it's really just a slight variation of DTV involving frequency or period, whichever you prefer. You could have the same calculation with period. I mean, speed is equal to 2 pi r divided by period. You could solve for the period here instead of the frequency and done it that way. It really doesn't make any difference. Now, what's kind of interesting is we've got things like frequency and period, which were quantities that were introduced to you guys in your waves unit in grade 11. So what do they have to do with circular motion? Well, mathematically, it's kind of nerdy cool, but they actually sort of all tie together. So when you guys did waves last year, something like this, you know, you had period and you had frequency when you did waves last year. And mathematically speaking, that wavy type structure should actually look familiar to you as well from math class. Because if you take this that type of shape and you would graph it, that looks an awful lot like the graph of the sine function or the cosine function. If you graph them, they will look like this. They actually create a wave. And that's one of the reasons, like the trig function, like sine and cos especially, are often referred to as wave functions, because when you graph them, they will actually make waves. But if we continue to connect this as well, often when you guys learn your basic trig functions, especially like your 30s, your 45s, like your trig ratios, the specialized trig ratios, you often learn them on the unit circle, and you guys do specialized angles and stuff like that. And there's your circle. So it's kind of weird, but these things all tie together, whether it's the circular motion stuff, connects to trig functions, connects to wave functions, all these things kind of web together, and they're sort of like these underlying properties, in this case, the period and frequency, which actually can connect all of these things together. So it seems kind of mathematically nerdy weird, but that's the reality behind how these things sort of can connect together. All right, so that's why things like period and frequency, which you guys took in waves, can actually then connect to the circular motion stuff that you guys are doing right now.